Okay, okay. For working in this wonderful place where such kind of a lot of math is going on. So really excited to hear and discuss with a lot of people. So let's talk about this work that was initiated by Juan, then that was extended for the varieties from physics, which is the geometric synthesis. So what's geometric synthesis about? So let me maybe start with the kind of tools that I use that is geometric theory. And these tools are maybe coming from representation theory itself. Let me say some words about this. So let's cheaply compact thing that we work. Then, well, whenever you have a classic group, okay, first, whenever you have a finite group, you have different kind of shape of functions you can put on V. So, first one, maybe just continuous functions. Let's call it V, right? Representations. Functions. You also have this basically smooth functions, locally constant functions. In the middle, the structure of a p-degree group gives you something else, something that is also just depending on the fact that it is a p-adic manifold, and this is the shape of the space block dynamic. So you can think about these two extremes as basically just a spatial function you can attach to any group. It's nothing special about it being company group. And the object in the middle, something that actually depends on additional structure on G, meaning locally just a bunch of copies of the p-adic. So just to recall what a local analytic function is. F is local analytic. If locally on G, say isomorphic copies of numbers, this function F on the detox of F can be basically the equation of convergence functions. Just notate on all the this one would be here because locally constant function, locally just constant thing, locally with the power series, and power series like that are going to define the continuous. So from these discrete types of functions, we can study different kind of representation here is functions. They give rise to different representation theories. Of course, continuous functions concerned with continuous representations. Spaces. Smooth functions are just the usual smooth or locally constant representation, maybe just representation. And in the middle, we have this category representation that has been maybe first studied by maybe starts already studied by Lazar, and also studied by Esteban, which is this category of locally analytic representations. So how classically these representations are detected? I mean, whenever you have some kind of topological representation of the group T, how you can decide in which this category is going to land at? Well, the continuous representation G B, let's say, lands in one of these categories. Well, let's say that more or less the same, starting with the orbit line that takes very big amounts to the orbit. It was a function from B, from B equal to B. Inside the correspondence space, they are continuous functions. B that maybe because I say that everything is continuous, that it's kind of automatic. You can just write on this technology. The smooth representations, well, this one space of the smooth function from B to B is just the space of local functions. So basically, this orbit is going to define a locally constant. The smooth representation is basically every orbit is locally constant, the definition. And then in the middle again, you have this kind of spaces of local functions. So representation is going to be local analytic as long as the orbit is given by these local power series. Okay. So the question is, we have these category representations. People have studied, well, using maybe graphical techniques of Markov analysis. Well, when study maybe these two extremes, this one is basically the pure algebra, so we can deal with pure algebra instead. But this ones we actually need some tools for analysis. So the question is, how to geometrize things? Something that we learned maybe from algebraic geometry is that usually representations of relative groups or representation of different kind of groups, algebraic groups, that are basically encoded in the category of quasi-continuity of the stacks. So the question is, can we actually hook up these categories, maybe some enhanced versions of these categories, out from some geometric incarnation? So I think question. So, well, maybe for this one, it's not difficult. Basically, you can do algebra and do something to obtain these categories just in algebraic geometry. But for this two, it's what I need to know now. Okay. Have analysis, you want to encode the actual topological representations. You need to involve topology and representation theory.
A question to understanding what are famous representations.
For example, yes. Yes. So ambiguous representations are going to live over, for example, some kind of logical ring, so we call beta algebra. But could be, I don't know, more fancy expressions of rings, depending on the kind of thing. But yes. Right. We don't want to just take the smallest class of representation for this is reasonable, that may be called the admissible representations inside. We actually want to have a very rich theory where we can do basically any kind of reasonable algebraic procedure and still present it. So for this, not surprisingly, these days, we need a maybe because of the nature of these representations, all of these corresponds to non-archimedean analysis, so we can even go a little bit more specific and go directly to say solid QP mechanisms. So, well, Gaussian Schulze and this category of math. Okay, say much about that, but just say that for things like political rates like QP, we have a nice theory of complete modules of tensor. It's set up such that, for example, tensor products of Banach spaces give you the usual product, and tensor product of Berger spaces give you the usual projective tensor product. So it's a very nice category that algebraically is the best thing you can expect, and a linear category for limits for limits and so on. And that is still for classical things in codes the correct kind of algebraic operation to approach the spaces. So CLA continuous functions. This guy, the whole the QP algebras. Even better than not just the QP algebras, but because of the computation of the group, they are even top algebras. So a whole algebra algebraic geometry is automatically it's a spectrum, it's a commutative pop algebra. Algebraic geometry, the spectrum is going to define a group just because the action of being a pop algebra is just the dual actions of being a group. I'm assuming I have unit and a people. So these guys, then they define again this wall for this math, we does not have like nice framework of topological vector spaces, but also talk about the geometry. More precisely, talk about analytic geometry. So whenever you have a ring in some kind of complete theory of modules over that ring, you are basically giving the data of an affine object in this category of analytic stuffs. So these guys, they define say, analytic groups. The sense of Gaussian Schulze that I'm going to denote typically by the G continuous. But yep.
Sorry, what's the co-multiplication action on these guys? Sorry, what's the co-multiplication about?
It's induced by the multiplication map. Whenever you have this map, you have a map on the other side from the functions, from the continuous function from here to the continuous function.
Oh.
And this one turns out to split in the principle. So G continuous is basically, well, basically by definition, going to be the spectrum that again, this is essentially pure notation, it's just the geometric object represented by this ring spaces by the scheme of continuous functions. We have also a locality. This is a purely
okay, for us it's a simple.
For us, it's simple. Yes. It's essentially just the opposite category of this. Yes. You can think about this basically as a spectrum, but not at the points of the ring, just at the shift that it co-represents in the category of affine scheme. More like a categorical incarnation of affine scheme. We also have this local identity incarnation corresponding to this local identity group. And we have this small incarnation corresponding to so again, maybe I told you that all these things come not just this algebra, you need to specify the category of complete modules of this algebra. What we're going to do is just call it QP algebra. So we are always working on this. So
Of course, the right language. That's where I have to believe this. But if this water is where do these spaces live from the naive point of view?
in naive point of view, there are just let's say this one is a backspace.
Yes.
This one is just a polylimit of an dimensional vector space. And this one is a polylimit of Banach spaces.
But it's
look at
for instance, in the middle
transition.
With respect to compact, in particular, they are not embeddings.
These
They
are
are not closed.
Yeah, they don't have no closed transition path. Yes. This is one of these nuclear LPS space of compact bed. I think this is kind of the classical. Just a co-limit of bank spaces where the transition maps are compact. So again, now we have different groups. Yep.
So first off, do we make any assumption that the image of the orbit has to be in a finite dimension?
I mean, maybe in here I never define what this is. But well, no, actually just the smooth function here. I think that it's going to be automatic that the image of the orbit is going to be that. Because it's calculated to an open subgroup. Given a vector, I mean, not the whole thing. But given a vector, the orbit is going to be in that finite vector space. But there is already an open subgroup that trivializes the vector, and the group is compact.
For the smooth case.
For the smooth case, just for the smooth case.
Just for other cases.
Yeah, for the cases, it will be very good.
So, for instance, an infinite direct sum of representations is okay. So you're getting representations.
And I will define it. I'm going to define it.
But whatever it is, it has infinite direct.
It has all coordinates, all limits. It's the best thing you can expect for algebraic. Yes. I mean, it's going to be algebraic categories. It's actually, yeah. Okay. So from these groups, you will get maybe the right category. It's not right. Patients. So the first one, maybe it's going to be the right category of the spin, or you can think about these basically of the homonyms. These continuous functions. But with respect to these kind of complete tensor product, which is the solid tensor product. We also have this category of local analytic complex. And also have this category of again, the way you realize it maybe more quickly terms is as commodule of this complex. It turns out that maybe any kind of classical notion of the local representation actually is going to embed this notion of the orbit landing in here is basically the same data as a commodule object for this whole algebra. So this kind of point of view from the orbits coincides precisely with this view of commodities.
Is it the case that these guys we defined earlier didn't define, but CILA G B is the same with QP tensored with V?
Tensor with V.
So if you take look like
Yes. Basically, this one, yes, for the V's that it was referring here to the tensor product, this tensor product, and in the most weird cases, so again, this one is defining groups in analytic stacks. So whenever you have a group, you can classify a stack, and these are just the category of quasi-coherent sequences. It turns out that this geometric approach, this kind of way to construct fields of representation, actually enhances the let's say more classical approach to representation. Some other remark is that you have these functors. This, well, again, I told you that the smooth functions are inside the local analytic functions. They're inside of continuous functions.
So what are the maps? So you have three groups.
Yes.
In somewhat places. And what are the maps?
Yes, so the maps corresponds basically because these ones come from algebras, the maps corresponds to just arrows in the direction of the algebras. And this tells you that any smooth function is locally analytic and any locally function. So it's just the inclusion of the map the other way.
But just in order not to get right the arrows.
Yes.
But
that so continuous go to the local analytic, the local analytic. A way to remember this is basically if you have maybe at the level of stacks like this here, you have a smooth representation. You can forget the structure being smooth, and any smooth representation is local analytic or constant. And if you take a pullback, any local analytic is going to be continuous. So the pullback still matches the fact that continuous by local analytic.
Sorry, what are the analytic structures of those guys? Are these just solid modules which are also
Algebra objects, or yes, visual objects. Okay, so from different features of representation theory, we can express it basically by studying these functors, like pullback or push-over functors, stuff like that. For example, this push-over functor is like taking a smooth vector or something, and it's going to be a G, maybe, I don't know, funny remarks. So the pullbacks, just making forgetting essentially. Also, we have this star, which is basically taking local analytic vectors. Well, basically, all the vectors that would work in this local analytic has possibilities, more or less, in that. And this guy is basically just a real algebra component. This taking smooth vectors. Variant actually points at the algebra. So you can still say something like that. For example, of this, if you map to the point, get this, so you can recover one of these Lazarus theorems saying that for finite representation, continuous homology is the same as local analytic homology, the same as like homology of the algebra, the algebra homology. What you hear is actually you have this enhancement with basically everything just because you have this. So this is indeed a powerful tool. And yes,
That flows down. I mean, you wrote the Lapid is derived.
yes, it's right. Okay. So we have the representation theory, and then the articles theory. Yes.
Is there a reason why restrict the compact groups instead of?
Just to write down this. Otherwise, it's going to be an union of. Otherwise, are not going to be a fan. You take something that is not compact. So this is just the right one. Otherwise, it's because.
that's right. Those graphic labels are they like limits when you take the shrink power of G?
Yes. Yes. Both of them, yes. Right. So the question, the path representation theory. We want to apply representation theory to study many things very never have a rigid space. We can cover the rigid space by different means, for example, using some kind of proetale torsions like that. And a way to study like sheaves, these proetale torsions, which turns out to be just objects of invariant theory. So we like to use representation theory. So is there some version of this? We are diagram for rigid spaces. Sorry, not that, but something that put analog. Maybe continuous right G continuous, local analytic, and smooth. If I forgot the continuous, it's because I look at the analytic group and we found 3 different incarnations of Higgs. What are the possible incarnations? Not one incarnation, but the other theory attached to a rigid provider. So let it's be smooth rigid space over, let me take just radically close to C. And the answer is, well, Yes, there are analogs, and let me just write down what the analogs are without mentioning briefly what they are. But by an example, that just write in a second. So yes.
Sorry, can I have something? Here you mentioned like those category, right category of position.
Yes.
You already have a with moving body.
You have that's a good question. This one is going well, the pullback is going to be a fully fed phase. This one. So being localized is actually just property category. But this one is not a property. This one is actually a structure. And the reason is because basically you have kind of the algebra conversion. So you need to specify how the algebra acts even if you are bigger.
Yeah, but thanks for that. But also, I'm kind of wondering, like, you have like, actual representations. Here you have the right category. So what's the relation of top and bottom?
I mean, this one is going. I mean, maybe you're a nice category of this one. There I didn't specify some vector spaces. But for original representation, these are just going to conventionally painful.
The H naught to get the classical.
Yeah, this one is. I mean, each one of these has a nice T structure, and these are the right category of the T structure. So have a.
Is it important step or here? I don't.
It's a theorem.
It's not. I don't see why it's important.
It's I mean, it's a theorem. You can make it not too hard using the geometry. You can make it more hard using like more representation theory point of view. But basically, the idea is that somehow for this functor you have projection formula. So put the forward so it's here. And the local analytic vectors of the trigger representation, which is the trigger representation. So this is again, it's not
okay. So for instance, we have to understand. So no problem. It's clear if you work with if you understand the word representation in some traditional sense. But
the data for any traditional sense, all these complete tables. Yes, all the complete tables, even the smooth value.
So it's not. It's a theorem, and one has to understand the definition.
Yes.
And the geometric property of the stack. So you have a morphism of stacks, which you know by F.
Yes.
Already you have a morphism.
Yes.
Is there a geometric property of F, which is
Yes, it's basically the push forward of the unit is the unit. And this is basically implied by how F was big between F over star and the push forward of the unit. We have to do these conditions whenever you have some 6-point formalism, you automatically is going to have a fully favorable. So there is a automatic property in code this theory of 6 pointers.
Okay, so but the fact that for instance H star, it's also a theorem. It's not. Is it true for G? So which of the two properties value for G?
For this one, the second one, because we are taking the algebra homology of the trivial representation.
And what about the first one?
This one. The first one. Okay.
Is it proper?
Yes. So you have analog of this, so let me quickly write this. Conversion of this is basically when rising diamonds, it's like perfect spaces, everything is continuous, Banach, nothing else. Play with. You have the variety X, then this mysterious X. I mean, this is very smooth. In here, we get something that we're going to talk in the next lecture, maybe the geometric seminar, which is this analytic drum stack. here, but some other object that on this analytic and Hodge-Tate. And let me not say exactly what these guys are. Instead, let me, in an example, say what you can compute them.
So anyway, there is an announcement. There are such
Yes.
factors, but at this moment we don't have to understand what they are.
No.
But he will.
I want to write
Please,
an example of how these things can be computed. Basically, this is how I, let's say, got induced into trying to of this project of this guy was because of the following example.
What is the first involved?
Yes, I know.
It's a diamond or what?
It's a diamond. It's a diamond. Let me explain.
What are assumptions? See?
What?
What are assumptions on the fields?
Those are the Berger flows. Of course, if you have rich space, it's the Berger-Colmez.
It's not directly close to the
Right. I mean, doesn't matter if he's the Berger, just so one of the Berger. So then let me give an example. Well, these things can be computed like this. So say that have a prototype cover where this guy can give some kind of group or that is infinity, let's say. Then when the way you compute the diamond of a real space, you cover by perfect spaces and just pin down the perfectly the equivalence relations mapping into that. In this case, the perfect space is X infinity and the equivalence relation is G. So this diamond is going to be X infinity as a perfect space. But then, when you think about G as a perfect space, you think on G as the spectrum of the continuous functions. Here you should have this. I mean, we specify what kind of G you're working with. This is the way you think of it. For introducing the other two, let me maybe just following instruction. So let O is infinity, the shear functions, let me add big one, not one for three. Then we have an action of G as on the shift, meaning that for any superspace stabilized open to group of G, we have an action of functions this. So we have an action of G of the space.
So suppose, for instance, the X is basic function, right?
Yes, for example.
And now the question is which so there are three incarnations.
Just not the continuous functions.
The continuous function, yes. Local, yes.
Yes.
So you cannot just take the quotient of X infinity by G per A.
No.
Because GLA doesn't react.
Exactly. This representation is not local, it's just a binary representation. But trying to solve that, let us take the local analytic here. So let OMA be the subscript of locally analytic vectors. Okay, this is just here. And also inside here, then just take a smooth shift from smooth vectors. Then these ones are going to be low with natural topologies. And so we'll be able to form some kind of yes.
Some local analytics object.
But you need some capital.
Yes. G was like as before. Very.
But the group is not a structure of property.
The natural property, yes, it was all situations.
Well, it can be. Well, it can be propagated. So.
This OXLA, for example, is that the drive?
Just taking the 19 just to make sense. Let us just take the most of just the local interpret. Turns out that in many cases just would be that the right ones and just would be the ones. Out of this I can construct things like kind of more generalized version of quantum spaces. Or just like stacks. Just more general version. That's well, it's not too far from just thinking about this as basically being the local space or the non-direct political space with the perfect one and they shape about it. So this is not basically it's not it's not the definition, but it's not the way to think about that is that it's not. Okay. We can also consider the smooth versions.
And what are the directions?
So again, the direction of the arrows because the algebras when it's right there, then it's for the opposite ones.
Now, when well, the stack, so do emphasize the analytic steps, not analytic space.
Because there is no notion of analytic space.
Because, well, of course, they are not analytic spaces in the traditional sense. But is the problem that is it because points have automorphisms or for different reasons? Well, my friend Dennis Genscoria calls everything a pre-stack. Once Victor asked him a question, a simple question, that Genscoria started answering, consider a pre-stack.
Yes.
But so of course the topological truth, since the notion of analytic stack is so general that is it are there really spaces but more general than
there is, yes. I mean in this the Ramstead paper, well, I introduced a notion that looks pretty much like analytic space.
So these analytics, they are analytic stacks, but they are not really stacking.
They are not really. I mean, you can do them in some kind of analytic topology by just rings. Like you don't need to make some kind of weird functions. So these are not like these.
Open stacks not because they are motions with respect to actions which are completely stabilized.
Yes.
But simply because the previous notion of space were not general.
Basically, as I understood, there was no like consensus.
Based on steps, but these steps are not so steps.
No. I don't like it.
Because there are some other steps, or they will appear, which, for instance, these steps are really stacky.
Yes.
But these are not.
These are not stacky. Only statistics.
Exit can be smooth as something like just the kind of inverse limit of the finite level.
So if I write maybe this one, let me emphasize that this one is really right one. Then what's different than this one? But the actual limit is Higgs. Basically, it's just the calling of the functions for each mass element.
So in particular, if I work with some example like the
inverse. So the inverse becomes the normal is the same as. And this is the curve because this guy is basically just the co-limit of the rings. So
So look like this.
and these two are the development functions. General could be.
Wait, just to make sure. In the case of torus.
Sorry, go ahead.
In the case of torus, what describes the function of x nuclear analytic?
It should, in that case, coincide with the smooth ones, but it's a particular case. It's not like general. In general, you could have a local effect. Like for more varieties, you would have local effects. But let me continue and the total will appear. So we have these spaces. That's some problem from these things, and okay, let us just well, we have these three styles, right? Point over continuous, point over related, point over smooth. So let's just apply it. So I say that we have a map of these diamonds. State Higgs. This one was just this 6 infinity modular continuous. But then I can take these locality vectors, and then now this group is going to appear, and I want to take stack. And let's say this one is going to here. Let's take one of some hypotheses. Let me not say this yet, because it's going to be related with the reverse of both. And this one, well, basically is just gravity descent that tells you that this is what this. Right? But the problem is at the wrong start.
Basically all information about the spaces can be ordered in a kind of local system that they would consider was my initial here.
So this torsion is already always called by a local system, a proetale local system. So this particular space is
yes, but you have different class of local systems. One, well, for the bottom one is those that are would develop by some finite coverings.
yes.
And others is some category of local.
Yes. So these ones are maybe not too interesting. There's going to be kind of forgiven shapes. These two are going to be much more close related. And if you look at vector bundles, they're going to be the same. So vector bundles are always locally analytic, at least from the point of view representation theory. But not all representation of vector bundle is true. Okay, and well, then I promised that there was some kind of a wrong stack here. But actually, this one, I mean, this one looks like an analog of the smooth version, but you should think about this one as the actual analog of the smooth version. So this one, again, I'm going to explain yet, but you can define the wrong stack for perpendicular spaces. Broadly speaking, what you do is you take this perpendicular space and you model by some kind of over-convergent diagonal these things. And still, you would have this kind of problem. This one is. So
but this is not the most efficient way of defining the rams.
It's not. It's a way to compute it.
Well, maybe.
I mean, this one. No, this one has.
My understanding is that if the RAM has something very
Yeah, it has. Yes.
And of course, it's nice to have such a difficult description for all cases, but actually, the RAM is not so surprising.
Yes.
The other guys are surprised.
Yes.
And moreover, so this is kind of not a definition, but a description. It's not so good as a definition because you have to depends on the choice.
Exactly. Okay, so infinity energy. But this is just how to compute it. So let me talk about this hypothesis that you make. And these hypotheses are actually encoded into this that we call the medicine.
And this is a hypothesis of what? It's a
the geometrics and operator that I'm going to mention now.
So is it true that the functors, these constructors, experiment XAG, they as a function for area, let's say, small feature?
With these descriptions,
No, not the description.
no, general defined for the two definitions are
yes, these are definitions for poor people.
The two definitions are quite general. You don't need any hypothesis.
But the description works under certain assumptions.
Yes.
And this is assumptions of X or an assumption on the presentation of X as function of the integration.
Yes. But then, at least to have this presentation.
Yes, is the second.
Yes, maybe it's the second. Yes, depends on the presentation of Higgs as a function of a perfect space. But this additional assumption, at least right now, conjecturally should be enough that this guy is perfect. But a priori depends on something that is not even Higgs infinity. Depends on something that is, I mean, what I mean is that this equality does not depend on Higgs infinity to be perfect. It depends just in this geometric set theory. But the other equalities, well, this one actually depends on nothing. This one also maybe doesn't depend on nothing, but this one depends on being perfect.
Yes. So now, what is the relation between the words geometric set theory and the words under some hypothesis?
In geometric of this also. That it's got theory. I'm going to explain right now. So for this, maybe let me talk about the geometrics and operator. So let me start with the Hodge-Tate panel. Product side of this. Right, the local system and depends on the factors. Let me also take B sides. Then we have the following theorem. Right. Theorem is initiated by Juan, curves, then so the resistor and all the linear map with a B will be to be just of Higgs omega 1 is 1. Just a big reason. I very close to matter, but let me just remember there. Again, this one is allowed for the sheets. With the following properties. First, maybe this one is not the formation of this tutorial will be and Higgs by Kubas. You might be separated, but things are going to be important.
Sorry, it's an operator that is on.
It's an ordinary value in Higgs proetale. Kubas. Property is that this guy is a Higgs field, meaning that it equals to 0, and also it's a derivation in that terms of this. So R is 0. This is 0. Okay. Which forward B is a vector bundle on X. Same rank. This case. Basically, the full bundle. Basically, this guy is going to be 0 if and only if this vector bundle already comes with space, and it's not something new. Before.
So right now your X is essentially defined over CP.
But it's not important. Just over C. The last property that I could not here, but and then just change the more. Here.
So this is a kind of abstract. Yes.
Yeah, that's the structure for this not to be zero. The last one is that actually you can compute prototype homology. Model. By current computing the homology in this guys for the Higgs field, then just forget the results. These guys molecules of so this guy here is called the geometric system. So Stuart is telling you that whenever you have a vector bundle in a proton side, always with a vector bundle, there is a natural structure of this as a Higgs field. Maybe not over Higgs, but it's maybe what you would like to say from the perspective that is in correspondence, but in the proton side itself, there is Higgs field structure natural on this that actually detects whether or not it comes from rich space and detects and computes proton topology. So
this looks very familiar with like oil and other people's genetics.
yes, I mean,
What's the relation?
I think they use this.
So
This is they call it the canonical Higgs field. This is geometric system, right?
I think it was in this part where you said that like spectral model, right? Attached to some proetale local system, that like there is some natural way of attaching Higgs.
Yes, yes. So you can look at the space of Higgs fields in the proton side, and there is natural section for like vector bundles, even by this geometric system.
that means that this is a one directional proetale vector bundle to all of these.
Yeah, there is this one. If you have the program, it's going to have section.
On the theorem, do you want to say that the state of is like the unique operator that satisfies all this?
Well, and we construct a canonical operation.
Yes.
Satisfy, probably it's not even it's just statement, but it's a statement that we have constructed a canonical.
Yes.
You have constructed a canonical operation which satisfies the function.
Yes, yes, yes. Then not the uniqueness statement to the construction. In the case when we have a source by a valid group, or how much time do I have left? Just to be sure. At least half an hour. Okay. For when we have a valid group, we can say them more. So we get into this one.
Sorry, just make sure. Here will be this map here all over proetale sites. It's not over another. This map here.
Yes.
In fact, all over proetale sites, not over another.
In the product side, yeah, this statement is just in the product side, not in very fast. I mean, you can make it more faster. Just the product side, this. So let's go back to the case of ortho. Hold that. P6 infinity, G, X. So don't know that this statement is not just true for bundles, it's true for a larger chips that somehow locally analytic exercise. Maybe not, let me say what that means, but let me just say what that means. Let B be a locally analytic representation.
So in this by in the part,
Yes.
there is no X. So there is not, it is kind of additional
Yes.
data for
How maybe.
Maybe not of the.
No. It's actually something technical phenomenon that you get.
Yes, but this theorem is wrong.
No, you don't need it. Then let the Yaroka interpretation of G, and for simplicity, that is Banach. Could be calling this Banach. And everything but what is proven and stated. And let is beyond the line in a cheaper. The total cycle just defined by this set. Have a continuous representation of G and always descend to sky to a relation, the product. So G. Then here, consider well, this one still has a Banach space structure, so we can consider this completed, but our module, and this guy the matrix and operator. Theta B but maybe the properties you're going to still preserve it basically 1 and 2. Well, 3 is also not part of the input, which is 1, 2, 3, so 24 is something like that. I don't know, actually, I think the all of them is like sorry. 1, 2, 4.
There's a mode of you write it.
Yeah, just with that part meaning that it's actually completeness of
Over
over 50, yes, over 50. There is a natural set operator on this kind of case that well, to extend the case of vector bundles to these local linear representations. Satisfying the same property there, so you compute proetale homology. Can detect when something actually comes from the panel level thing. Basically, when this stuff not smooth vectors. And
So the difference between this year and the previous one is that now your B tensor of X hat is bigger.
yes, basically that's the only difference so far.
what was the
difference is just that it right now is much bigger. It's not just a vector bundle.
it
Can be infinite dimensional, yes. And this I'm going to right now the new part. Moreover, there is a math that I like from this field that is infinity. Rule of the diagram again with a joint representation. This is the joint action. A representation, as you see, this is a proetale shape over X just by descent in the joint action. Diagram. Thank you for that. This mouse based on the problem. So I have this vector bundle. These are very big representation.
So when you say actual action, it's something
minus 1.
but it's where is the actual action something which obviously exists and
Yes.
So it's not a separate. Wait, so just can you? So the fact that there is a natural exception is not separate.
I think he's just saying take V to be the adjoint.
Yeah, I
And
didn't
apply the previous.
sorry, I don't.
Just a special case.
Take V to do the joint representation.
No, not B. This is the algebra. The algebra of the group is the part natural. It's not B, it's the algebra.
Yes. There is a map such that.
Yes, I want to. Now, so you can differentiate B.
If this is not within the omega one, we got rid of the filling out of this omega.
It's a different math.
It's a different math.
It's not theta V for any V.
No, this is one like something I call theta. It's something that always depends on the source. And this map, well, first you can take B and you can differentiate B. I say the local representation, you can differentiate B, construct this connection. And then you can apply this map. And this produces mapping. The same thing for the things, but they always such that this map precisely is the
So like the usual sin operator is like from like BG to like some like period ring of like CP or whatever, or some period ring. So then like, so I see the lead G here, and so like, is the thing on the right somehow like a period ring?
I mean, the sin operator is mapping into CP, just the complex numbers. But CP is basically just the O hat of the proetale side. So it's
So the statement is that the situation is we can be admits the particular way. Now in this diagram, each arrow is are there arrows in this diagram which are more surprising?
I mean, this one is just the derivation, it's not very surprising. Just
This is
the derivation.
so the horizontal arrow is not surprising.
Yeah, this is just to take a local representation and to take the derivation by the end.
Yes, and what about the vertical?
This one is maybe the surprising one, because this one is the arrow that comes from the previous theorem that is attached to any kind of shape like that. I told you that this representation comes from a local representation. Basically, everything is just depending on the dorsal. Like this guy only depends on a kind of universal derivation.
Yeah, so
This one is surprising.
is it the vertical arrow which is surprising, or is it the commutativity of the diagram?
I would say that well, basically both statements are surprising. The fact that you can this one can describe it universally in terms of a single arrow. But maybe just to mention the comment that we had before. Or we have that or we have that this maybe not this. So well basically sketch that theorem 1 implies theorem 2 is the so basically V is a local analytic representation, so you can always embed it in your map geoequivariantly into local analytic functions of P depends on the V. Well, depends on the rotation, but maybe this one I write regularly. So for the sake of proving this statement, because the construction of these guys is natural, we basically do the physical space. And then I say that in the statement, the representation has to be finite, but you can just take 40 minutes of 1x and you respect each one of them and let me just with again the right vector. So then theta d acts. So theta d has a joint called d, which is the joint of this map from this one to there. Going from the time space, that was 1. And so this O hat B, I mean O hat B. And this map taking any vector here and acting in this principle there. Let me say by what thing here, but let me just have finished this. Perfect. This guy makes this time space acting by O hat linear derivations. There, the derivations that are left G, but they are just depending on the local system as a right representation, and you still have the whole action on the left. So well, this is just a well-known pattern in the space, and you look at this kind of representation, but they need to pass through a map. That, yeah, the graph. And let's say we do a list. Oh, again, maybe surprising, but once you know these properties, it's not too hard to do that.
So I think the statement of this last theorem,
yes,
is going to diagram on the right. You also want to be here.
Sorry.
On the right, when you have the vertical arrow, yeah, you want B's to be
You want V to be
underlined.
Yes, 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 yes.
Because otherwise,
Yes, yes, yes. This guy, this is not all about that. Sorry, I forget something. That's all. So then, well, maybe let me say the following colors, please. So the first one is that if you take sheaf of localizing functions of an action of the here around these by derivations, maybe itself. And well, apparently the same operators functions through a map like that. Everything is all that. So you can always take locality vectors and you produce information that mean set operators. And this guy, he also this here. So this is what the Louis calls I don't know, it's a dimension like for the infinity and etc. by
Then didn't the method.
is yes, it's a map from the tangent space to the Lie algebra. And here I'm taking the whole half and claim that this map already exists, you just take Docker and anything. And it's saying that this one is acting by derivations, or here by that, and that this space is going to add trivial from here. So more geometrically, or maybe let me say that comparing with the previous,
And this operation ends where? So
in these sheet by derivations. If the algebra acts by the data, then you can extend derivation just linearly.
yes, but then you say that so Sen is an operator from where to where.
Maybe just say this. Set of the minus statement one as a whole day. So the image of this map here, which are just a bunch of next operators here.
Sure. This fact eventually reduces to computational power stuff.
This one?
Yeah.
No, I mean the construction of these operators reduces to that. But this one.
But to check this particular fact.
No, this follows formally from this step. Just by some kind of change variable. I mean, you just study this representativity. This will follows like this. By this step. Let me go back.
So this is this a way to distinguish the local analytic functions or general component is significant. It's hard to follow.
So let me say what this significant is maybe in terms of this complex. Yes, what is significant. So for this, the first thing is that but maybe it doesn't work for this directly. Actually, yeah, maybe for this is that this guy is going to be this infinity LA modulo GLA if only if this map from the algebra logic complex is symmetric.
For example, you mentioned a certain condition.
Yes, and this is the condition.
The whole
Exactly this condition. And if you have this condition, even this local analytic vectors are going to be derived and so on. This is basically what you have. And even better, well, basically because it's subjective, some kind of consideration to make an argument. This tells you that what you have a natural map from this. Basically, I tell you that the kernel of this map, more or less that the automorphism of this map, corresponds to precisely those differential operators that are treated here. Right? That this guy is acting by G. G acts in the whole space, it doesn't matter, but the only difference is what happened for the Lie algebra. And basically, the only thing that killed the Lie algebra because of this map is going to be tangent space. So this tells you that this guy is going to be a germ for, let me just say more for this. And this one is the overcomponent. I also like to write it. This one is this overconvergent neighborhood at zero of the tangent space. So this is similar to the
representation of X. So you have things which depend on
this is taken by
X, and there are things which also depend on the representation of X.
Yes.
Motions of something by G.
Yes.
So your statement is true.
It is independent of that presentation. I just saying that you can see that statement, for example, using that presentation.
But anyway, this statement too is an important fact of life.
Yes.
It has nothing to do, probably there could be several ways to prove it, but anyway, it's true. You're saying that it's true.
Yes. And maybe what I want to highlight with this is that somehow the first kind of evidence we saw about this analytic Hodge-Tate stack in a geometric way was broadly speaking because after studying this local analytic, somehow because this geometric Sen operator is secretly encoding this Gaussian space by acting equivalently here. And under these conditions of the Sen operators, this particular representation is a germ for this time space. So it turns out that actually this presentation is just a particular chart that you have for the Hodge-Tate stack. In general, principle of this Hodge-Tate stack is going to be a germ for this operator.
Yeah, New also has this notion, I think it calls locally analytic cover. This is not related to.
I think this is the same as that.
That's the same.
Yeah, I think that's please introduce it.
Because then it's a germ and it's an abelian germ.
For that, it's not going to be obvious that it's a abelian germ. For that part.
And if it's an abelian germ, then it's banded by well, spectrum, it would be banded by something. And it's banded by some analytic.
Yes, some kind of function.
And you
but I didn't say what it is. What? I didn't say what it is. I just said
okay. But is it the best small neighbor because
Yes, it's the analog of the formal completion at 0, but in rigid.
But so my understanding is that it's analytic more precisely the version of the analytic then you have not only formal neighborhood, but you also can take the intersection of the whole.
Yes.
Of course, these words are meaningless. It is the classical analytic geometry, but in the new version, they're needed.
Yes, sir.
And well, I would say even them, if they require efforts to define themselves and visualize.
Yes. So as Vladimir said, this guy is essentially the intersection of all neighborhoods.
The intersection of all neighborhoods. Is it known by dagger or yes, and dagger it's wonderful.
Yeah, I think that
well,
intersection of all these things. Yes. Yeah, maybe this is like a very wrong for it because we're specifying what kind of what is the subspace for which we are taking all the neighborhoods. Taking the intersection of all subspaces continuously. Yeah. Maybe this one is more precise than this.
Let's see. Because we've got a lot of questions, about 10 minutes.
Okay. So maybe let me just not mention what you can do with these more varieties, but instead just sketch the way you construct these operators. Recall that we start with V, some kind of OHAP module. That one, yeah, Berger-Colmez, the statement was vector bundle, but also could be one of these local analytic things. That's what we don't have. Well, we want to construct this array. So the first thing we do is we look at this upnoise, maybe with a chart. Please. Then in this case, basically V, the datum of V, determine when we just write down something before. So we have this chart. We can consider the first vectors. Pull back, I'm going to X infinity, going to be X equal to this group. Okay, group gamma is isomorphic to just copies of okay. Then V is already determined by what? By its points here and its equivalent action.
Just to clarify, this X infinity is different from that X.
Yeah, it's not the same X infinity. This is the general stuff. This one is the one for this. I mean, so this V was chosen, was a vector bundle. Vector bundles in proetale side of smooth. The spaces are the same whenever you have a perfectly covered as those vector bundles in this perfectly covered plus its equivalent action. It's the same as categories. Turns out that for this kind of shapes, you also have this kind of descent response. Basically, this one you can do recover both of these. So now we have this object there. And again, we have all this theory of all this representation theory behind it. So, well, the first thing we can do is take maybe just local analytic consider. And let me maybe just keep the note in V instead of all of that, just put these points. PLA. There's local analytics. Gamma local analytics. Then, after set theory, Berger-Colmez that then can be extended to this kind of things. Implied basically that, well, this guy is a module for the local analytic functions of this guy. Yes. And if I just extend the scalar to its infinity, I will cover the V itself. So basically, set theory tells me that I can complete this thing using these local analytic vectors. So this is what all these computations with traces and stuff are playing a role. Tells me that you can do that. But even more, again, abstract set theory tells you that the local analytic functions for this particular cover of a perfectly thing, or maybe pullback of a perfect cover, is just the smooth of functions. So this means that the action of the V algebra here, there, here. In other words, that the V algebra is just linear for this OLA. So then in 3, you can consider just the derivation. And then just extend it. Again, just because we got because it's linear function, we can just also it's gamma equivariant, so we can just forget about OLA and get something that so far looks like that. Not that the adjoint representation in the algebra of gamma is just trivial to gamma squared. So this is kind of the local construction of these operators. The difficulty in this thing is basically these abstract things in theory is the diffusion theory. But then there is a problem that this is a computation depending on some charts. And you basically want to draw this the whole space. So how do you do that? Then, on that by Schulze, know that the first molecule had given by mega 1 600. Not this splitting of the Hodge-Tate homology, even if not the spectrum very complex, we have a little degeneracy of the spectrum. This is, well, applying this kind of thing was a remark that Juan mentioned to me. Okay, just send it here. So basically, this tells you that completely that the homology of gamma of these functions is the first homology group isomorphic to the space of the orbits. Okay. But then again, we have all this fancy representation theory, maybe 10 theories, something like that. This is continuous homology. And I mentioned that continuous homology can be computed as a locally analytic homology. But this, because the local interpretation can be computed as a D-algebra homology and invariance. This is but the D-algebra is trivial here. This is just to give you a isomorphism between this and this. And whenever you have basically two different charts, the way the set operators are going to change here are basically going to give you the same cycle that defines this vector bundle. So you end up just gluing this using this isomorphism and glue everything to this the humanity. Fine, so let me just finish now.
Given the time issue, let's maybe ask the speaker afterwards. Let's speaker there.
Also, let me make a quick announcement. I think next week